Bond energies are one known value of thermodynamic data that can be put together to know a heat of reaction. Because we could know the energy required to break or make each bond, we can put that all together for a specific experiment. When all of that is compiled and put together a little bit more, we also can create a set of data called the standard enthalpy of formation. This tells us how much energy is consumed or released when making a compound from its elements. So rather than needing to think about each step along the process, we could think about, relatively speaking, how stable is one compound, or how much enthalpy does one compound have compared to another. When we're discussing standard enthalpy of formation, it is defined as the energy exchanged when 1 mole of a substance is made from its elements in their standard state. The standard enthalpy of formation will often be given in a table, and it's given a lot of times with other thermodynamic data, including free energy or entropy. When we're looking at standard values, we are looking at the standard thermodynamic state. The element itself in either its atomic or its molecular form. So, oxygen gas, for example, would be O2, but helium would be He, or just a He atom, when we're at 1 atmosphere and 25 degrees Celsius. So, not STP, but similar. And if we're talking about aqueous solutions, we would be doing the calculations for those as if they are a 1 molar aqueous solution. We need to remember that this is about making a compound from its element. So every element would have a standard heat of formation of 0 to make something from itself, or we're comparing the compound compared to what it was before it was a compound, when it was in its elemental form. So this right here is a 26-page chart that just has lots of values for heats of formation. Your textbook or the online textbook that you might be referring to would have a much smaller but more focused table. And when you see these questions, like a problem right here, you would be given the specific values for each substance within the problem. And you would just need to know how to use and apply that to solve the question. This equation, unlike the bond energy equation, is given. So it's something that you will see, you will need to know how to use, and you need to make sure that we're remembering what goes where. An important difference here is this is products minus reactants. When we go to bond energies, it's the bond energy of the reactants minus products, because broken minus formed keeps our sign. Here, in a more traditional final minus initial, we do products minus reactants. So that's a very important difference to notice and remember. This one is given. We need to memorize this one and recognize that that one is the opposite.